Welcome back, everybody. This is our fifth class in JEE Mains previous year questions for chapter Dual Nature of Matter and Radiation of class 12th. Before this video, we have made four videos in this series, and all of those videos are available on our channel's playlist section. We have also started a similar series for NEET, so if some of your friends are preparing for NEET, you can guide them through those videos also. With this, and if you find this helpful, then do press the like button, share these videos, subscribe to our channel, and also like to donate us something. Scan the QR code in front of your screen. It helps a lot when you share and share some amount or donate some amount. So with this, let's start today's video. In the previous one, I think we covered up to something around question 50. Yeah, that was the last question. All the previous question I have cleared. Why? Just to save RAM in my PC because I have limited RAM, so it does not work great if I keep on opening multiple tabs. So with this, let's start with the question number 49 today. So, a beam of light has two wavelengths 4972 angstrom, 6216 angstrom with total intensity equally distributed among the wavelengths. The beam falls normally on area 1 centimeter square of a clean metallic surface. Work function is given. Assume that there is no loss of light by reflection and that each capable photon ejects one electron. The number of photoelectrons liberated in 2 seconds. So we know that number of photon incident per second are given by power by the energy. Now, power is we know intensity is basically power by area. So from this, we can write that power will be I times area. So this becomes IA divided by E. Now we have had two wavelengths. So what we can write that uh, first of all, we have to find out that whether both of these are capable of ejecting the electrons because their their energy should be greater than work function to do that. So E1, let's say, we know that energy is basically Hc by lambda. So E1 will be Hc by lambda 1. Now Hc is 1240 electron volt nanometer divided by lambda 1, that is 497.2 nanometer. Nanometer gets cancelled, and if we solve this, we will get 2.49 electron volt. Similarly, for the second E2, that will be Hc by lambda 2, and that will be 1240 electron volt nanometer divided by, that is 6 to 1 6 to 1.6 nanometer. And if we solve this, what we will get? We will get 1.99 electron volt. So what happens here? That E2, the energy of the second light, is less than the work function. So if it is less than work function, so it means that it cannot eject electrons. So we will not calculate for E2, we will only calculate for the E1 because only photons of first light will be able to eject electrons. So N1 will be equal to P1 by E1, that will be I1 into A divided by E1. Now intensity is distributed among equally both of these. So intensity of one wave will be half of that, that will be 1.8. So 1.8 10 raised to power minus 3 into that is area, and it was mentioned here 1 centimeter square, so 1 into 10 raised to power minus 4 divided by energy. Now here we need energy, this energy even we have calculated it in electron volt, but actually we need it in terms of joules. So this will be equal to 2.49, that is in electron volt, into 1.6 into 10 raised to power minus 90. Now it's converted into joules. So if we solve this, what we will get? We will get 0.4518 into 10 raised to power 12, and that can be written as 4.5 into 10 raised to power 11. The nearest match here is, that is 6 into 10 raised to power 11. Because only these photons will be able to eject electron. Oh, sorry. Wait a minute. A correction here. We have to find out in 2 seconds. So these are the number of photon incident per second. So in 2 seconds, we will get 2 into 4.5 into 10 raised to power 11. So that will be 9 into 10 raised to power 11 photons in 2 seconds, and equal number of electrons, because as mentioned, each photon is capable to eject an electron. So option A will not be right. Option B will be the right answer here. Moving ahead. A photon of wavelength lambda is scattered from an electron which was at rest. The wavelength shift delta lambda is 3 times of lambda. The angle of scattering is 60 degree. The angle at which the electron recoiled is phi. The value of tangent phi we have to calculate. So what we can do here? We can do momentum conservation. Momentum conservation. So let us assume this is an electron and a photon strikes to it. Now, after striking, what happens? That suppose this is our horizontal direction. Our photon gets scattered with angle 60 degrees. So this is our photon, and this angle is 60 degree. And here we have electron that is scattered by angle phi. So what we can do here, that we can use momentum conservation. So momentum will be conserved in both x and y directions. So if we write equation for the x direction, what we have initial momentum of photon plus initial momentum of electron is 0. It should be equal to final momentum of photon plus momentum of electron. That is the equation in x. So uh, now initial momentum of photon, what will be equal to? Momentum of a photon can be calculated using E by C, where E is the energy of the photon and C is the speed of light, assuming that photon was moving in vacuum. Because for photon, we have E is equal to PC. The actual equation is, let me write it, that E is equal to m square C 4 plus P square C square. For photon, mass is 0, so this terms get converted into 0. So from that we will get E is equal to PC, where P is the momentum of photon, and from that we can write uh, that momentum will be equal to E by C. Now energy of a photon is equal to h nu by C, and nu by C is basically h by lambda. So for photon we can write momentum will be h by lambda, and for, we can say, electron, let's keep for electron as it is. Now for photon we are writing it as P. So P will be equal to final momentum of, let's say, P final for photon this is, and for electron that will be PE. Now okay, sorry, wait a minute, let me write it PF, let me write it PE, and I have to take components here, because let me write that we are taking these momentums in x direction only. So initial momentum of the photon in x direction, we assume it to be P. Now final momentum of photon in x direction, that is PF cos 60, plus final momentum of electron in x direction, that will be PE cos of phi. Now similarly, if we conserve in y direction, so we can write that initial momentum in y direction is 0, and final momentum in y direction, that will be PF sine 60 minus PE sine phi. So from this, what we can write? We can write from the y direction that PE sine phi is equal to sine 60 is root 3 by 2. So root 3 by 2 of PF. Now what happens here? That wavelength shift is 3 times of lambda. Let me use different color here. And this wavelength shift is for photon. Means what I can write? That if initial wavelength lambda initial was lambda, then shift is 3 times lambda, or we can say lambda final minus 3 lambda initial is 3 times of the lambda. So 3 lambda. So from this, lambda final will be 3 lambda plus lambda initial, that is lambda. So that will be 4 times lambda. Now what we can do? We can use this lambda to calculate the momentum. So initial momentum, that was P, it was h by lambda for photon. For photon, final momentum will be h by lambda final, and lambda final is 4 lambda. So h by 4 lambda, and this comes out to be P by 4. We can use it here. That P is equal to P final, that is P by 4, into cos of 60, that is half basically, plus PE cos of 5. Now from this, what I can write? That PE cos of phi is equal to P minus P by 8, that becomes 7P by 8. And also we can substitute value of PF here in this one. Oh, sorry. So this becomes PE sine phi is equal to root 3 P by 8. So we have these two equations, first one and second one, divide both of these two. So from that, what we will get? We will get PE sine phi by PE cos phi is equal to root 3 by 8 of P divided by 7P by 8. So P by 8 and P by 8 is cancelled, and PE is cancelled. So from that, tangent of phi is basically root 3 by 7. Now root 3 by 7 is 0.247, and that is nearest match to 0.25. So option C will be the right answer here. Now moving in the next question. The anode voltage of a photocell is kept fixed. The wavelength lambda of light falling on cathode is gradually changed. The plate current I of the photocell varies as. Now what we can do here? We can use idea from the photoelectric effect. We can use idea from the photoelectric effect. So in photoelectric effect, what we have? We have maximum kinetic energy is equal to energy of the incident photon minus the work function, and that is basically hc by lambda minus phi. So what happens here? It is mentioned that wavelength is changed. So let us say first we are increasing the wavelength. So if we are increasing the wavelength, what will happen? Energy of the light or energy of the photon will reduce, because energy and wavelength are inversely proportional. So if energy is reducing or energy decreasing, so what will happen? That after certain value, the energy of the incident radiation will be less than the work function. So there will be no electrons ejected, and if there is no electron ejected, means current will stop. So if we keep on increasing the lambda, current will stop after some time, and that happens in option A, but does not happen in option B. So B is rejected. Similarly, C is also rejected. So we are left with option A and D. Now, if we keep on decreasing lambda, what will happen? If we keep on decreasing lambda, then energy will keep on increasing. If energy will keep on increasing, we can say maximum kinetic energy will keep on increasing. Now, here is nothing mentioned regarding power of the incident radiation, because number of photon is basically E by P, and as in here in the graph A, we can say if lambda is decreasing, then intensity decreases and goes to zero. Means there is no current, but that will not going to happen, because if we keep on decreasing lambda, energy will keep on increasing. So we will get photocurrent. Photocurrent will be there, but there is no mention regarding power. So we cannot conclude regarding intensity, but what will happen to it. So, but from the option A, that here intensity is going zero, so that will not happen. So we can say A is also rejected. So only suitable behavior which we can find, that is in option D. So move ahead. In experiment photoelectric effect, student plots stopping potential versus wavelength, reciprocal of the wavelength. So V naught versus 1 by lambda for two different metal A and B. These are shown here. So looking at the graph, you can appropriately say that. So we have to find that which of the statement is right. Now, first of all, what we will do? We will find the equation which satisfies this graph. So we have EV node. So EVS, sorry, stopping potential is equal to energy, that is Hc by lambda minus work function. So I can write it like this, that Vs is equal to Hc by E times lambda here minus phi by E. So this is like Y is equal to mx plus c. Now here m, that is slope, is equal to Hc by E, and intercept on the y-axis, that will be negative, that is, sorry, c intercept, that is minus phi by E. So from this we can see that slope, in slope we have h, that is constant, c, that is constant, E, that is constant. So slope of both of lines should be same, and here we can see that both have different tails, both different slopes. So means either data for A is wrong, or data for B is wrong, or data for both of them might be wrong. We are not sure. So let's see the options. Work function of metal B is greater than metal A. So we cannot conclude that, because for that what we need, uh, uh, for that we will need their intercepts. Let me draw that, what type of information we will need. Let's suppose this is our axis, and here we have the negative x, negative y axis. Now coming to the first line. So suppose this is the first line and this is the second line. Wait a minute. I have to increase the length of this one. Yeah. Now I think both of these are parallel. So if both of these are parallel, means their angle, this is also theta and this is also theta. Now I can compare their work function. Now this will be the intercept of first one. So this will be equal to phi 1 by E, and this will be equal to phi 2 by E. Only if these thetas are same, then we can compare their work functions. So option A is not going to write here, is not going, is wrong basically. For light of certain wavelength falling on both metal, maximum kinetic energy electron emitted for both and A. So for maximum kinetic energy, what we need? We need to find the work function, and we cannot calculate work function because they both don't have the equal intercept. So B is also rejected. Work function of metal A is greater than B, so that is also rejected. So only conclusion we are left with, that student data is not correct. So that will be the option D is the right answer here. Moving to the next one. A copper ball of radius 1 centimeter and work function 4.47 electron volt is rated by UV radiation 2500 angstrom. The effect of radiation results in emission of electron from the ball. Further from the ball with equilibrium charge, and due to this finite value of potential on the ball, the charge acquired by the ball. So what will happen here, that suppose we have a ball here. We have a ball and let's fill it. That's light. This is our ball. Now what we have? We have incident photons on it. So when photons incident on this ball, what will happen? That electrons go out like this. When the electrons go out, they will leave positive charge on the ball. Now there will be a scenario that this positive charge will be at certain value, that it will not allow electrons to go outside. So for that scenario, what will happen here? That potential acquired by the pole will be equal to the stopping potential. So that is the basic key concept here. So for that, what we have, that E times Vs is equal to Hc by lambda minus phi. That is the basic equation we have. And from this, stopping potential can be calculated as Hc by E lambda minus phi by E. So let's calculate. So 1 by E, let us take it common. Now Hc by lambda we have, so that will be 1240 electron volt nanometer divided by lambda, that is 250 nanometer, minus work function 4.47 electron volt. So if we solve this, what we will get? We will get stopping potential as 1 by E 4.9, I think, yes, 4.96 minus 4.47, and that both are these in electron volts. Solving this and cancelling electron, EV means, we will get 0.49 volts. This is the stopping potential. Now we have to calculate the charge acquired by the ball. So charge acquired by the ball, how we can calculate? We can assume that ball will act as a capacitor, and for a spherical capacitor we have Q is equal to CV, and for spherical capacitor C is 4 pi epsilon naught times radius into potential. So from this 4 pi epsilon naught, that we know it will be 1 by 10 raised to power 9, 9 into 10 raised to power 9, and so this will be 9 into 10 raised to power 9 into radius. It is given to be 1 centimeter, so 10 raised to power minus 2, 10 raised to power minus 2, and potential, that is 0.49. When we solve this, we will get 5.4 into 10 raised to power minus 13 coulomb, and that is nearest to option A for us. So option A is going to be the right answer here. So with this, moving to the next one, this equation has statement 1 and this equation also, this question should be has statement 1 and statement 2. One of the four choices given in the statement, choose one of the best described. Davison German experiment established wave nature of electrons, and we know that is basically right. And electron have the wave nature, they can interfere and show diffraction. So we know that wave nature was shown by Davison German experiment, and particle nature by photoelectric effect. So this shows wave nature, and we know that wave can show interference and diffraction. So we can say both of the statements are right here. And statement second explain the statement 1. So option C will be the right answer. Photoelectrons are ejected from the metal when light of frequency nu falls on it. Pick the wrong statement from the following. No electrons are emitted if frequency is less than the W by H, where W is the work function. So that is basically right. Ejection of the photoelectron is instantaneous. Yes, it is instantaneous, means the time actually is around 10 to the power minus 8 seconds. So this is almost instantaneous. Maximum energy of the photoelectrons is h nu, and the maximum energy of the photoelectron is independent of the intensity of light. So from the photoelectric experiment equation, we know that maximum kinetic energy Ke max is equal to h nu minus phi. So as we have a non-zero work function here as per option A, so if work function is non-zero, so maximum energy cannot be equal to the energy of the incident photon. So option C is wrong here, and that is the we have to find out wrong statement. So option C is the answer for this question. Coming to the next one, this question has one and two statement. Okay, so statement one. Metallic surface is irradiated by a monochromatic light of frequency nu greater than nu naught threshold frequency. If the incident frequency is now doubled, the photocurrent and the maximum kinetic energy are also doubled. So it is mentioned that frequency is doubled. So if frequency is doubled, so what we can write that Ke max is equal to h nu minus phi. That is the basic equation here. Now, as per the statement one, that incident frequency doubles. So let's write kinetic energy as K2. Let us write as it is as Ke node is equal to 2h nu minus phi. Now, if I take ratio of both of these, so Ke2 by Ke node will be equal to 2h nu minus phi divided by h nu minus phi. Now this can be written as 2 minus phi by h nu divided by 1 minus phi by h nu. Now what is phi? Phi is basically h nu node. So this becomes Ke2 by Ke node is equal to 2 minus nu by nu node divided by 1 minus nu by nu node. Now it is known to us that nu is greater than nu node. So means nu by nu node is greater than 1. That is the basic assumption here. So what we will do, let us take as zero point 0.1 this ratio. For just sake of convenience, let us take as 0.1. So this can be written as 2 minus zero point 0.1 divided by 1 minus zero point 0.1. So this will be 1.9 by zero point 0.9, so that will be 19 by 9, and that will be greater than 2 because 9 to the is 18, so it will be greater than 2. So means kinetic energy will be increased more than 2 times. It will be increased more than 2 times. So as mentioned here that maximum kinetic energy are also doubled. So kinetic energy is not doubled, so we can say it is means it is actually increased more than 2 times. So statement 1 is going to be wrong here. The maximum kinetic energy for electron emitter surface is linearly dependent upon the frequency of the incident radiation. The photocurrent depends on the intensity. So from this relation, we can easily write that kinetic energy is proportional to frequency. So it depends linearly. So first part is true, and coming to the photocurrent, we know that photocurrent only depends upon the number of photons striking per unit time. So that is basically intensity. So statement 2 is right here. So 1 is false and 2 is true. That is option B. So option B is the right answer here. Moving ahead. So again, we have two statement question. A metallic surface is irradiated by the monochromatic light source of frequency mu is greater than mu naught. Threshold frequency, maximum kinetic energy and stopping potential are Ke max and V naught respectively. If the frequency of the incident radiation is doubled, both K max and V naught are also doubled. So we just solved it previously that kinetic energy does not doubles. So statement 1 is wrong, and the reasoning behind it you can watch in the previous question. The maximum kinetic energy and stopping potential of photoelectron emitted from the surface are linear dependent upon the frequency of incident radiation. So for both we can write that Ke max is equal to h nu minus work function and also E times Vs, where Vs, the stopping potential, is equal to h nu minus phi. So from this we can easily write that both kinetic energy is proportional to frequency and stopping potential is also proportional to frequency. So statement 2 is going to be right here. So 1 is true and 1 is false and 2 is true. That is option C. Moving ahead, again two statements. When ultraviolet light is incident on a photocell, its stopping potential is V naught. The maximum kinetic energy is K max. When the ultraviolet light is replaced by X-ray, both V node and K max increases. That is the statement 1. Statement 2. Photoelectrons are emitted with speed ranging from 0 to maximum value because of the range of frequency present in the incident light. Now we know that X-rays frequency of X-ray is greater than frequency of UV radiation. So energy of X-ray will be greater than energy of UV radiation. And if energy is greater, then it means maximum kinetic energy of ejected electron will be greater and stopping potential will also be higher. So we can say statement 1 is going to be right here. Now coming to the second one, photoelectrons are emitted with speed ranging from 0 to maximum value because of the range of frequency present in the incident light. So that's not true here. That is going to false. But because why? What we are doing here, when we discuss photoelectric experiment, we normally what we take monochromatic frequency. Sorry, monochromatic radiation means which has only single lambda, single wavelength. Or in the if even if we are solving some questions, even then we maximum cases we take two lambdas, lambda 1 and lambda 2 for their just comparison, and they are not simultaneous. Even they are not, also not simultaneous. They are irradiated one by one just to as per the question, just to check, just to compare. So for a monochromatic radiation, we have single lambda or single frequency. So kinetic energy will be constant. So in conclusion, one will be true here and second will be false here. So that is option D for us. Moving to the next one, the surface of a metal is illuminated with a light of 400 nanometer. The kinetic energy of the detected photoelectron was found to be 1.68 electron volt. What function of the metal? So we know that Ke max is equal to h nu minus phi. So metal is illuminated with 400 nanometer frequency. So we can say energy or h nu will be equal to hc by lambda, and that will be 1240 electron volt nanometer divided by 400 nanometer. So nanometer gets cancelled, 0 gets cancelled, and what we have 3.1 electron volt. And maximum kinetic energy is 1.68 is equal to 3.1 minus 5, and if we solve this, what we will get, phi equals to 1.42 electron volt. That is option A for us. In the next one, wave property of electron implies that they will show diffraction effects. Davis and German demonstrated that this by diffraction electron from the crystal. The law governing the diffraction from the crystal is obtained by requiring the electron wave reflected from the plane of the atom in a crystal interface constructively. See figure. Electrons are accelerated by potential V are diffracted from a crystal. If D is 1 angstrom, angle of incidence 30 degree, V should be about. Now, what is we are going to use here? We are using basically you going to use Brogue's law of diffraction, and for that we what we have condition. The condition is basically n lambda is 2d sine theta, and we can also drive it. And actually, let us drive it so that there is no doubt regarding how this relation comes. So let this be a crystal structure. And this be our normal. I think it will work fine. No, it will not. So I have to choose different color. Let's say black. So this is our normal to the surface. Now let's take an incident radiation. Let this is our incident radiation. Actually, we are taking a plane, a wavefront. So like this, and then it is going outside like this after reflection. So what is happening here? What we can do here, we can find the path difference between these two lights, and for that let's mark it like this and like this. So now let me explain what I'm going to do here. So suppose this is A, this is O, this is B, this is C, this is O dash, and this is D. So as these are the two light rays and they will be interfering here at some point on the screen. So to solve the interference, what we have to do? We have to just calculate their path difference. And if we see, their path difference will be this COD dash line or light has traveled this much path extra. It has traveled this much path extra. So what we can do, assuming this angle to be theta, and this is the atomic spacing, that is d, that is given here. So this one will be equal to d sine theta, and this distance is also d sine theta. So total extra path difference, that is you can say delta x, is equal to 2d sine theta, and for interference, for maxima, it has to be equal to n lambda. So that's how we get this relation. So now let's start to calculation for finding out the potential that we have to calculate. So now we know that lambda is basically h by p. That is the de Broglie wavelength for the electrons, and it can be written as under root 2 me h by 2 under root me, where E is the energy required, and energy required can be written as 2m charge times the potential q times v. So from this, squaring both sides, lambda square is h square by 2mqv, and from this potential comes out to be h square by 2mq times lambda square. Now value of h we know, value of lambda I think we have to calculate here. Yeah, we also know for the diffraction that lambda has to be order of atomic spacing, and here spacing is around 1 angstrom. So we can use that value. So this will be 6.626 10 to the power minus 34 whole square divided by twice mass 9.11 10 to the power minus 31, charge 1.6 10 to the power minus 11, and atomic spacing, that is 10 to the power minus 10, and square of that. Now from this, what we will get? We will get 1.5 into 10 raised to power 2, and that will be approximately 150 watts. Now if we see, there is no I can say option that is comparable, that is exact match, but 50 volts is the most comparable answer, or the most nearby answer we can get. So we will go with option B here. Moving ahead, this part, this is the same question, means same question in the previous IIT questions, JEE question. There was some question which depends upon the same paragraph. So these both two are related to each other, and the part here which we have to try, where we have to find out condition for maximum, and that we have already solved. That is n lambda is equal to 2d sine theta. So n lambda is equal to 2d sine theta. That is option C here. Now moving ahead, photon frequency mu has a momentum associated with it. If c is the velocity of light, the momentum is. So we know from the general theory of relativity, you can remember this equation, that E square is equal to m square c4 plus p square c square. Now for a photon, mass is 0, so this equation reduced to E is equal to pc, and from that we can write momentum is basically E by c. Now E is the energy, so it can be written as h nu by c. So option A is going to be a valid answer here. And this can also be written as, we know that C is equal to mu lambda. So nu is C by lambda. So if we substitute it, that it becomes H by lambda. So only option A matches here. Moving to 63rd, the threshold frequency of metallic surface corresponds to energy of 6.2 electron volt. Stopping potential for a radiation incident on the surface is 5 volt. The incident radiation lies in. So we have to find out that in which region incident radiation will lie. So stopping potential is 5 volts. So 5 ev should be equal to 6. So that is threshold here. So E minus 6.2 electron volt. So energy of incident radiation should be equal to 11.2 electron volt, and now we know E is equal to Hc by lambda, and from that lambda is Hc by E, so that will be 1240 electron volt nanometer divided by 11.2 electron volt. If we solve this, what we will get? We will get something around 110 nanometer. Now we know that for visible spectrum, what we have? We have 400 nanometer to 700 nanometer. Now, beyond this, here with increasing wavelength, we have IR infrared, and for lower wavelength, we have UV. So, 110 is below 400 nanometers, so it should lie in the at least in the UV region, and for X-ray region, we have wavelengths in the angstrom region, in the angstrom region of the scale. So only option A is viable. Option C and B are straightforward rejected, where visible and infrared are given. So let's move to the next one. Yeah. The time taken by a photoelectron to come out of the photon strikes approximately is. So the time taken is of the order of 10 raised to power minus 8 to 10 raised to power minus 10 second, and this is almost instantaneous. So the answer will be option B here. Let us move to the next one. The anode voltage of a photocell is kept fixed. The wavelength lambda of the light falling on the cathode ray is gradually changed. The plate current of the photocell varies as. Now we have covered this a similar question like to this. Now this is 65 question, question number 65. I think it was a question something around 50, which we solved. Yeah, here it is. When we found out that if we increase the lambda, then energy will decrease, and if energy decreases, then maximum kinetic energy will also decrease. So the only possible answer was, that was option D for this one, because after certain wavelength there will be not enough energy for the electrons to get ejected, and so current should become zero. So if lambda is increasing, we can say current should become zero, and if lambda is decreasing, current will not become zero, as in case of option A. So from that, only option D was a viable option, and in this scenario also similar type of graph will be a viable answer. Let me go to that question. Yeah, here it is. So the only viable option will be option B here. Now let's move to the next one. A photocell is illuminated by a small bright source placed 1 meter away. When the same source of light placed is half meter away, the number of photoelectrons emitted. So we know that number of photoelectrons are proportional to number of photons striking, and number of photons are equal to power by the energy, and we know that power intensity is equal to power by area. So basically power is I times A divided by multiply E, where E is the energy. So now regarding this formula, from this you can see, you can miss or wrongly interpret that number of electrons emitted will be proportional to area. So let me explain it clearly. Suppose this is our source and this is our we can say plate which will emit electrons. So it will emit radiation in all directions. It will emit radiation in all directions. Suppose it's let's say it is in circular shape. So we can take radius. So its area will and its radius is small a. So small its area will be pi r square. Now suppose this is the distance, that is capital R. So the intensity reaching here, suppose I know we can say P node is the original power which is emitted by the source. So I reaching here will be equal to P node by 4 pi r square, and the energy that is incidenting on this plate, because this I is going in every direction uniformly, so we can say that energy will be equal to, and this will be the energy per unit time, or basically power delivered to this plate will be P node by 4 pi r square into pi r square. So basically the power delivered to the plate, or the energy per unit time delivered to the plate, is proportional to the area of the plate, or the radius of the plate square, divided by the distance square. What is that? Divided by the distance square. So as mentioned here, that we have decreased the distance. Initially it was 1 meter away, now it is half meter away. So the area of the plate is not changed. We have changed the capital R. Small r is not changed here. So what we can write, that number of photoelectrons initially was proportional to 1 square, and now they are proportional to half square. Now this is the energy per unit time. This will decide how many photons will be there. So basically this is our P. This is our P. This will decide how many electrons and photons will be there. Don't misjudge it with this E. This is the energy of photon. It will stay same everywhere. And this is the energy incident per unit time. Basically this is power. So this term is power, and this E is energy of the photon. So now if we divide, we will find that, let us say Ne dash. So Ne dash by Ne will be equal to, oh sorry, it was 1 by capital R square, because small r square is constant. So it will be, let me rewrite this. This will be 1 by 1 square and 1 by half square. So this will give us 4. So number of photons increases by 4 times. So that is the option. It is coming near, so number of photons will increase because intensity will increase. Moving to the next one. A radiation of energy E falls normally on perfectly reflecting surface. So the momentum transfer to the surface is, we know for a absorption type surface, momentum is transferred is E by C, and for reflecting type surface it is 2E by C. This is from the kinetic theory of gases. We have kinetic and Joule nature of matter and energy, and also I think kinetic theory of gases it is covered. So this will be 2E by C. Now, according to Einstein photoelectric equation, plot of kinetic energy of the emitted photoelectrons from the metal versus the frequency of the incident radiation give a straight line, and whose slope we have to find out. Now we know that kinetic energy is equal to hf minus phi. So this is the equation, that y is equal to mx minus c type. So its slope will be Planck's constant, and it is constant, so independent of everything. So depends upon nature of the metal is the same for all metal and independent of intensity. So option D will be the right answer here. Moving ahead, the work function of a substance is 4 electron volt, the longest wavelength of light that can cause photoelectron emission from this substance is approximately. So we have to find longest wavelength and work function is given. So we know that E is equal to Hc by lambda. From that lambda is Hc by E. So 1240 electron volt nanometer by 4 electron volt get cancelled and this will be 310 nanometer. So option A will be the right answer here. Now let us move ahead to the second last question we have. Two identical photocathodes receive light of frequency f1, f2. Velocity of the photoelectron coming out are v1 and v2. Then we have to find out relation between v1 and v2. And photocathodes are identical means their work function will be same. So if work function is same, then we can write that half mv square is equal to half mv1 square hf1 minus 5 and half mv2 square is equal to hf2 minus 5. Now if we let's say if we subtract both of the equation, what we can write m by 2 into v1 minus v2 square is equal to h f1 minus f2, and from this v1 minus v2 square will be equal to 2h by m f1 minus f2, that is option A for us. Moving to the last one, sodium and copper have work function 2.3 and 4.5 electron volt respectively. The ratio of wavelength is nearest to. So here it is not mentioned which wavelength. So what we will consider? We will consider for the threshold wavelength. Threshold wavelength, basically lambda node. And we know that lambda node will be equal to hc by E. So lambda node is proportional to 1 by E. So lambda node 1 by lambda node 2 will be equal to E1, that is 2.3 divided by 4.5. This will be basically 2 ratio 1, approximately, sorry, 2 ratio 1. That is option C. So with this video is complete. Hopefully whatever we have covered is helpful to you. Again, if you have any doubts or suggestion, put them in comment section. I will try to resolve them. And if you have not watched our previous video, then you can go to playlist section and watch those videos and playlist which we have already catered for you. And like to donate, scan the QR code. It helps a lot. With this, again, thanks for watching, and we will meet in next video.